Okay, good afternoon, participants all over the country and people who are seeing it on webinar. Next 1 hour or so, we'll be just trying to understand some of the aspects related to the hyperspectral remote sensing data processing. Basic elements that will be just touched upon are data reduction, feature extraction, and endmember selection. So, as I just mentioned earlier, let us get on with the task. Before we speak any of the 3 items that were mentioned earlier, let us just have an understanding what is that we expect from this hyperspectral data. We have been using remotely sensed data, we have been extracting information, so on and so forth for last so many years, but what is that something more we are going to expect from hyperspectral data? Most of the time, the remotely sensed data has been used for feature detection, then we migrated to do some kind of classification based on spectral characteristics, then discrimination, and also to identification to some extent. But what is lacking today's multispectral data sets is systematic characterization and quantification to determine the abundance of materials. Of course, it is a misnomer to say that abundance of materials is something new, because some kind of classification we are doing, but all the time we expect the pixel to have the single class in it totally. But that is not the end of the story. We like to go to the finer detail. That is possible because the variations in the material composition has potential to produce shifts in the positions of the at different wavelengths, and these absorption positions or the reflectance positions, they basically form the spectral fingerprint of the features. If we can exploit to the maximum extent these spectral fingerprints, we will be able to better quantify the remotely sensed images. And that is possible with hyperspectral data sets. That is what we like to deliver as an end product to the users. The entire gamut of data processing chain is, you get a raw data, whatever, whether it is an aerial platform or a satellite platform, whatever it is, then you have to undergo some kind of radiometric correction, which is out of the purview of the normal users. Then the user component starts from geometric corrections, atmospheric corrections, data or noise reduction, and information extraction. In fact, we will be concentrating on the data or noise reduction, information extraction components in next 1 hour. What exactly mean by data reduction? The kind of advances we see in electronics as well as the optics have resulted in the development of very high sophisticated sensor systems, which have resulted in information overload. When you want to deal with large volumes of data, the traditional statistical methods, they break down simply because you have number of observations, and each of the observation has got large number of variables associated with each of these observations. And just to put a point in perspective, the dimension of the data is the number of variables that are measured on each observation. And these hyperspectral high dimensional data sets present many challenges, and major difficulty is not all the measured variables are important for unraveling the phenomena of interest. When you have an image, you may not be interested in knowing everything in the image. You may have some specific information you may be looking for. All the variables or the bands, to say so, may not be contributing equally in extracting that piece of important information. So we need to handle that situation efficiently. Therein comes the data reduction component. When we just put in a simple mathematical framework, given any p-dimensional random variable, we have to find the lower dimensional representation of it that captures the content of the original data according to some criteria. Here you have large number of bands, to say so, and you have to find subset of the bands such that you will be able to capture the original information content, but For doing so, you need to have some criteria. Now, the key here is what is the criteria that you want to use to compress the data from large number of dimensions to lower dimensions, or large number of bands to fewer bands. We will just spend couple of slides to understand what is this specific criteria can be. The commonly used techniques are principal component analysis, minimum noise fraction, of course the recently introduced things like independent component analysis, so on and so forth. We will be basically spending maybe next few minutes talking about principal component analysis and minimum noise fraction. I presume most of the people are aware with principal component analysis because they might have been using with multispectral data, but for sake of completeness and also to bring and contrast the difference between the minimum noise fraction and the principal component analysis, the PCA will be touched upon. It is often known that when you have so many bands in the multispectral space, in the spectral space, the bands will be highly correlated and they contain similar information, and this correlation between the bands can be reduced based on certain statistical characteristics. And PCA has been one of the widely used techniques for dimensionality reduction as well as for data compression. And the objective of PCA is to reduce dimensionality in the data and compress as much of the information in the original bands into fewer bands. People who have used TM data, they might have invariably used PCA, so that your 6-band data from the bands can be compressed to 3 or maybe 4 bands. And these new bands, which are often called as components, they result from a statistical procedure. And here comes the criteria which that have been mentioned in the previous slide. The process attempts to statistically maximize the amount of information, or in other terms, the variance from the original data into least number of new components. And this maximization is based on eigenvalues which determine the significance of the principal components, and the data reduction happens in accordance with the associated eigenvalues. The first principal component shows the direction and length of the widest transect of the ellipse, as you can see in this slide on the left side, and the second principal component will be orthogonal to that, and third principal component will be orthogonal to the both. If you are having n dimensions data, then there will be n principal components, and each successive principal component accounts for decreasing amount of variation in the data which is not already accounted by the previous principal components. Although there are n output bands in a PCA, you will get n bands as output, but most of the information that is contained in the n original bands can be explained by first few bands itself. That is, the variance that is present in the original n bands can be explained by very few principal components, in some cases almost 100%. So in that sense, it is useful for compressing the data into fewer bands. Just as an example of this image, you can see this is the original data which is made as a false color composite using 750, 655 and 547 nanometer bands. This is PCA1, where it is most of the information that is present in the 224 bands is captured. Next is PCA2. Now this is PCA45. It is only noise. As the number of components increases, the noise increases. So most of your information is compressed in the first few bands itself. This is just another example. This is PCA11, which has got significant information because you can see structure of the various components, but the immediately following PCA12 is extremely noisy, but your PCA13 is again having a structure. This is the problem that is with the PCA. Although we statistically say that the noise should increase as we move towards higher bands, more often than not you may find some principal component which may be having some information of interest. So you cannot take it for granted that higher the number of PC component, it will be only noise alone. You can see the same thing with this PCA 20. 21 is again noisy, but 22 has got a lot of information. So this is one of the problems in using PCA. Another thing is, if you observe the principal component images, there is no illumination variation. This is Hyperion data. This portion is for in the across track direction for one line in the VNIR portion of the data, and this is for the sphere. You just have to compare this with the kind of illumination variations that will be shown in MNF case. Now, is the PCA good enough? Okay, it maximizes the total image variance, but it does not make any distinction between noise and information. PCA images are ordered by data variance statistically, but you may often find a component which may be of interesting information present. Then what happens if the bands have differing amounts of noise? Bands in a hyperspectral image have different amounts of noise, largely because your hyperspectral sensors, they operate in VNIR as well as in sphere. The sphere VNIR portion has got a separate set of detectors, separate electronics, totally independent component. Your sphere shortwave infrared has got a different set of detectors, different set of electronics. So even though at the user end you may get a composite stat, that manner in which the images are acquired because of their different optics and electronics, the amount of noise that is present in the different portions of VNIR sphere will not be same, and they may be related in a non-linear manner. Because of that, using PCA can cause this kind of discrepancies. That is point number one. Second, can we make any distinction between information and noise? And can we use some other criteria other than the eigenvalues for data reduction? Yes, we can make a distinction between information and noise, provided if we have dark images which are acquired in a shutter close position. That is, when there is no input radiance, only we read the electronic noise that is present. That can be used for estimating the noise present in the data. In the absence of dark image, if you assume that single signal at any point in the image is strongly correlated with the signal at neighboring pixels, this is basically because the landscape is continuous and there is a significant spatial autocorrelation exists. And while the noise shows only weak spatial autocorrelation, if you make this assumption, if you make a difference between the adjacent pixels, we will be able to arrive at averaged noise value, and this can be used to estimate the noise component that is present in each of the bands. The most common method of estimating noise in the absence of dark images is the method known as shift difference method. In fact, some of the content and the background that is being talked about is what is available for the users for quick to use manner in NV. So the most of this theoretical background is strongly related with the manner in which the implementation and usage in NV is offered by, so that it makes much easier for the participants to connect to what is being told in a theoretical manner when they try to use the NV functionalities. Because in NV also the MNF is done by using the shift difference method. It is assumed that each pixel contains both signal and noise, and that adjacent pixels contain same signal but different noise. Shift difference is performed on the data by differencing adjacent pixels and averaging the result to obtain the noise value to assign the pixel being processed. In fact, there are two ways of estimating noise. Either you can use the entire image to perform the shift difference method, or use a invariant portion or a homogeneous portion within the image and perform the shift difference method and arrive at the noise statistics. MNF is actually orders output components by decreasing signal to noise ratio. That is where the criteria, that is different criteria, is used in the case of MNF compared to the criteria of eigenvalues or the variance maximization that is used in the case of PCA. The MNF procedure first estimates the noise in each image band using the spatial variations in brightness values, then applies two successive principal component transforms. First uses the noise transformation to transform the data set to a coordinate system in which the noise is uncorrelated and is equal in each component. Then a standard principal component transform is applied to the noise adjusted data with output components ordered by decreasing variance. This procedure produces component set in which noise levels increase uniformly with increasing component number, and lower order components should contain most of the image information and little image noise. This is slightly statistically better represented than the PCA statistical method. This is an eigenvalue plot. If you can see, what we mean to say is the information which in the equivalent terms called as an energy can be compressed in a fewer number of bands or the components images, then you have captured all the available variability in the original data set. In this plot, what it shows is the 224 average bands can be compressed to 50 bands. Almost your energy becomes 1.0 at the when your MNF band 50 MNF bands are used. Means all the variability that is present in the 224 bands can be represented by 50 component images. In fact, this example shows if you have used the full image for noise estimation, your MNF1 image looks little hazy, MNF2 has got nice structural detail, MNF50 is totally noisy. But if you use portion of the water body for noise estimation, MNF1 is much cleaner. That shows the difference by the noise characterization using homogeneous areas provides better result compared with the noise characterization using the entire image. MNF2 also provides good amount of structural detail. As usual, MNF50 it is totally noisy. This just shows how the degradation of the signal all along the MNF components 1 to 47. This is a average Jasper Ridge image. As I was saying earlier, the hyperspectral sensors per se, they have a different set of optics and electronics of VNIR and SWIR. When the MNF is performed, either you can do a MNF taking the entire data set as a single stack, then the noise that is uncorrelated in VNIR SWIR can give unknown artifacts. The ideal way is if you are having two spectrometers which are operating in the VNR portion, say 450 to 950 or 1000 nanometers and 1000 nanometers to 2500 nanometers, then it is ideal to split the data into 450 to 900 nanometers as a VNIR data set, 1000 to 2400 or 2500 nanometer data as a SWIR data set. In case if the data is acquired by 3 spectrometers, wherein your 450 to 1000 nanometers VNIR remains same, but SWIR instead of acquired by a single spectrometer, one from 1000 to 1800 or 1700 and from 17 or 1800 to 2500, then it is better to segment the data into 3 to account for the manner in which the data collection happens. So it is prudent to segment the data into VNIR and SWIR segments and perform the MNF. In this case, for the same VNIR, if you are using only for the average VNIR portion, 25 components can represent the entire VNIR spectrum, and if you are using the SWIR portion separately, almost 30 components can represent the total energy. Means you are having actually 55 component images, whereas if you are using the 224 bands together, you may be having only 45 or 50 component images which may be representing the entire information content. So you are getting that additional 5 to 10 components depending upon the type of the image and the kind of the content in the image that is present. Little more number of components to be used. So whoever is using the data, they need to be little aware about the manner in which the data is acquired and accordingly split the data into the respective spectrometer segments, perform the MNFs and do a inverse MNF for SNR maximization. In fact, another interesting application of using MNF is to see how the noise in the image will be affecting your other related activities. In the first slide, we have seen the entire image extraction process has got one geometric component, which is a well-known thing, so I won't touch upon that. But the atmospheric correction is extremely crucial when it comes to hyperspectral data. You can do atmospheric correction by performing MNF or by not performing MNF. If you are using MNF on the left image, if you can see the water body area which is largely noise free, means your atmospheric noise is reduced after having reduced the electronic noise. So the quality of the image is much better. Whereas on right side, the electronic noise is not reduced. Keeping that electronic noise, we have tried to reduce the atmospheric noise, and you end up with significant amount of artifacts over the homogeneous water body area. So when you are trying to do information extraction, it is essential to lay down the processing steps. What is your end goal? How you have to go about by performing the activities in accordance with your desired result. And another interesting aspect, this is basically deals with the manner in which the data collection happens. As you are all aware, in optical sensors, we have push-broom sensors as well as whisk-broom sensors. And hyperspectral sensors also operate in push-broom. The EO1 Hyperion operates in push-broom mode, whereas the Everest is an airborne sensor, operates in a whisk-broom mode. When it comes to push-broom sensors, one of the common problems is you have something called spectral smile, which is basically relates to change in the central wavelength position in the across track direction. And the other thing is called knife edge, that is where your magnification or demagnification happens. The spectral smile is nothing, is strongly related, or in fact it is to say that spectral smile is due to chromatic aberration of the lens system, whereas the knife edge is related to the spherical aberration of the lens system. We don't go into the spherical aberration, we will just concentrate on the chromatic aberration because it has got some relevance in the application of information extraction. If you see this MNF images, the MNF1, which is acquired in 2002, the middle one is the MNF1 for the image is acquired in 2003, and the right, which is the MNF1 for an image is which acquired in 2004. This data is acquired by EO1 Hyperion 30-meter spatial resolution, which operates from 450 to 1000 nanometers in the VNIR, 1000 to 2400 nanometers in the sphere. What you see in the top right is the pre-launch calibration reference central wavelength, which varies across the field of view. That is, you have 256 detectors. What is the central wavelength across that? If you take the central pixel, that is the 128th detector as a reference, how the spectral wavelength is varying on either side of that central CCD at numbered at 128. This is why it is called as a spectral smile. Now, the MNF images, they actually represent this variation. If you see the 2002 image, if you draw a horizontal profile, it is almost matches with the spectral smile or the variations in the central wavelength in the pre-launch case. 2003 also, it is almost same, Of course, in 2004 it gets flattened out, which shows that there has been some change in the performance of the sensor system altogether. Now, if you have the knowledge that there has been a variation in the central wavelength, then it is necessary to correct that, because these central wavelengths are strongly related with your absorption band positions when you are trying to do the information extraction. Hence, a visual assessment of MNF1 images will give an idea how about the changes in the central wavelengths in the data set. Likewise, this is for the swirl image. In 2002 it shows a random behavior. In 2003 it shows an opposite behavior. In 2004 again it is a slightly random. Apart from data reduction, an assessment of the MNF images for preference sensor systems is essential to understand the changes in the central wavelengths. Just to have a recap of what MNF is all about, the noise is decorrelated. Data are projected to ion vectors of the noise covariance matrix. Data are noise lightened. Individual bands are scaled by noise covariance eigenvalues, and the data undergoes a linear transformation. If dark current bands are available, that is the ideal way to use it. Otherwise, use the shift difference method. Now, one more thing, when you are dealing with MNF, if you are using ND and you want to use a spectral hourglass wizard, then it is unwise to perform MNF, because this particular spectral hourglass wizard, it best performs MNF and then proceeds with the information extraction. If you want to use this hourglass wizard application, then the data should not be subjected to MNF. If you are having your own information extraction algorithms and you want to use the data with your own algorithms or some other functionality other than the spectral hourglass wizard, then you can perform MNF for doing information extraction. The next thing which has been recently talked about is independent component analysis. As it is well known that PCI and MNF are based on second order statistics, that mean and covariance or correlation. But many subtle materials which are uncovered by high spectral resolutions may not be characterized by second order statistics, because such samples may be relatively small and they may not be enough number to provide reliable statistics. In that case, ICS independent component analysis can be used, wherein the higher order statistics like skewness and kurtosis is being used. I am not going to any details of independent component analysis. I just given only a mention that there is one more method which is available. Now, the next topic will be image classification. In fact, the end member selection and image classification, they go hand in hand. So I will just give a brief for image classification, then we will talk about end members, then we will speak, we will have some mention about the image classification algorithms. When it comes to image classification, all of us are familiar with full pixel classification techniques. Many of them might have used MLC, then many of them might have used soft classification techniques. Then even with the hyperspectral data, when we talk about material abundance mapping, we are basically looking at subpixel classification techniques. Let us just have a look at this maximum likelihood classifier, which most of us will be using day in and day out. The key thing in this is you need to have mean vector covariance matrix. If you have these two properly defined and if the mean covariance matrix is stable, you can always calculate the probability. Now, what is this mean and covariance matrix has got to do with when you are having large number of dimensions. This, for doing an MLC, it is a well-known fact that the user selects some training samples. If you are using a Landsat TM data, you need to take some minimum 50-60. If you are using IRS list 3, you have 3 bands, so you may be taking 30-35 samples. That is the nominal requirement that we have to do. Now, if you are having too fewer samples, then your test data may be okay, but when you are doing the actual training data may be okay, but when you do an actual classification, it may not provide proper result. If you are having significant number of samples, your desired surface will be properly defined. Now the point is, how many samples are required to have a robust estimation of mean and covariance matrix. That is wherein lies success of using MLC. If you are having 3 bands or 5 bands, using an MLC for taking 40 or 50 samples may not be an issue. But will it be possible to do when you are having large number of bands? If there are n bands, then the number of elements to be estimated are n into n minus by 2 plus 2n. That is, if you are having 50 band data, means you need to have at least number of elements to be estimated to be around 5000. This will be the kind of complexity. If you are having more the number of bands, then the requirement of having number of elements to be estimated increases exponentially. But it is said that if you add additional features, when you say additional features, it refers to additional bands, your performance will increase or the classifier performance will increase. Yes, performance of the classifier can be improved by adding additional features, but it only improves up to a certain point, and beyond that it in fact shows deterioration. If n1, n2 are the number of samples, the dimensionality on the x-axis and classification accuracy on that, if your n2 is greater than n1, beyond some point your classification accuracy tends to decrease. So you need to have some optimal number. What will be the number of samples that are required for a robust estimation of your covariance matrix elements? For a linear classifier, the number of training samples should be proportional to the number of features for reasonable parameter estimation, if you are using parallelepiped or some kind of thing. For a quadratic classifier, which is an MLC, the number of training samples should be proportional to the square of the number of features. If you are having 200 bands, it will be manually impossible to have that many number of training samples. Then what shall we do? We cannot use MLC. Then the option is, you have to look at some alternate ways of doing classification. There can be 2 approaches, which we are all familiar with, the deterministic or the full pixel approaches, or the abundance mapping subpixel approaches. The total simplified spectral processing procedure, given your input radiance image, atmospheric compensation, which results in a reflectance image. Reflectance image undergoes data or dimension reduction. It could be MNF or it could be some other method. Then this image will be subjected to end user application. It could be either unmixing or it could be a simple target detection or a feature detection. Here comes, when you are trying to do this classification, we need some pure pixels. In the field of hyperspectral remote sensing, these pure pixels are termed as endmembers. These endmembers represent only one and only one feature type, and these can be collected a priori in the laboratory or they can be collected from the image itself. But how do you identify the pure pixels if you are not knowing or if you are not having any ground truth information? If you have a ground truth information, there is nothing like that. You can always match with your ground truth data with your image, take them as your sample sets. In the absence of systematic ground truth information, however, end members or the fused pixels will be identified. Several methods have been developed over the years. Some of them are in fact pixel purity index is the most widely used. Next comes the end finder, then sequential maximum angle convex score, so on and so forth. We'll just have look at pixel purity index. In fact, this is one of the most successful approaches. It is based on the concept of convex sets, wherein it considers spectral pixels as vectors in the n-dimensional space. For pixel purity index algorithm operates like this. It first applies dimensionality reduction using MMF. Then it proceeds by generating random n-dimensional vectors which are called as squares through the data set. Every data set is projected onto each of these unit vectors or squares, along which position it is pointed out. Data points which correspond to extreme values in the direction of a square are identified and placed on a list. As more squares are generated, the list grows and the number of times a given pixel is placed on this list is also tallied. Pixels with highest tallies are considered the purest ones, since a pixel count provides a pixel purity index. In fact, PPA algorithm does not identify a final list of n members. In fact, it is only a guide which to start with. These are the randomly projected vectors. These are the data points which will be projected onto the unit vector. The farther it falls and more the number of times the data point falls on that unit vector, the larger will be the score, and that will be taken as a pure spectra. In fact, this slide shows, and you can have n number of iterations, because how many times the data point has to be projected onto a random vector is not well defined. You can have 5,000 iterations or you can have 25,000 iterations. As you have a large number of iterations, it reaches an asymptote where it does not make any change. Probably one may have to use something between 15,000 or 20,000. You will get a reasonably good result of end members. This is in fact the PPA image. The brighter the pixel, the higher will be the count. This PPA image will be used with a n-dimensional visualizer to rotate and see the clusters of points and identify the classes in that n-dimensional space, which will be used for classification purpose. The other one is a n finder. The n finder method is an automated approach that finds the sets of pixels which define the simplex with a maximum volume. In fact, when you talk of a simplex, if you have a point, single point, that simplex will be a point. If you are having that simplex could be a segment. If you are having 3 dimensions, it will become a triangle. If it is 4 dimensions, it becomes a tetrahedron. If it is n dimensions, it becomes a polyhedron, so on and so forth. Here we are only showing for 3 dimensions, where these corners of this triangle are the end members. And the dimensional detection is also accomplished by MNF, and randomly selected pixels qualify as end members, and a trial volume is calculated. Trial volume is recalculated for every pixel by replacing that end member. If the replacement results in a volume increase, then the pixel replaces the previous end member, and this procedure repeats until there are no replacements of end members left. In fact, it is pertinent to say both PPA and n finder rely on spectral properties of the data alone. In fact, there are few more algorithms which also take into account the spatial position. In fact, I am not talking about those. I am only confining myself to the spectral properties based end member identification algorithms. However, n finder method is sensitive to random selection of initial set of end members. If the initial selection of is inappropriate, then it may take a very long time and high computational time will be required. If the initial selection set is proper, then it will reach a optimum solution in short time. But n finder is sensitive to noise. Another approach is sequential maximum angle convex cone. This is based on the concept of convex cone. This method finds extreme points in a convex set. Unlike the convex methods that rely on a simplex, the number of end members is not restricted by the number of spectral channels. That is the fundamental difference between the SMAC algorithm and the other ones. Algorithm for finding the end member, it is sequential. Convex cone model starts with a single end member and increases incrementally in dimension. And another major difference between the PPI, to some extent endfinder, and with SMAX is the abundance maps are simultaneously generated as and when the end members are identified. It is a loop back mechanism where one end member is identified, it generates an abundance map, then the next end member is identified. Based on the angle it makes with the existing cone, the abundance map is updated. Like that it goes on until no more end members are generated. In fact, this is also one of the tools that are available in NV. Now when it comes to the classification, it is full pixel or subpixel. There are variety of classification algorithms are available. Just to name a few: spectral angle mapper, backpropagation neural networks, or support vector machines, spectral feature fitting, spectral correlation mapper, spectral information divergence. In fact, list goes on and on. I have only listed just half a dozen. The full pixel classification, as we are all aware, and we have been doing this full pixel classification with MLC, we assume that single material is present in the image pixel, which is not true. One of the very widely used hyperspectral full pixel mapping algorithm is the spectral angle mapper, which compares unlabeled pixel with reference spectra in n dimensions, and the reference spectra may be obtained from ground-based spectrometer or from the image end members which were discussed earlier. Smaller the angle between the reference spectrum and the unknown spectra, the better will be the match. But here the key is how much should be the angle, which is defined in radians, should be used. If you use too small an angle, most of the image will go unclassified. If you are using too large an angle, there will be huge misclassification. The ideal situation is to use something between 0.05 radians to 0.1 radians, where you will get optimal classification is possible. And another good point about the SAM is illumination insensitive. In fact, this is variance in illumination. This is the original data. This is spectral angle mapper in the middle and maximum likelihood in the lower. This portion where there are illumination variations, they don't get classified in MLC at all. Whereas SAM, the entire patch gets classified as the same class despite illumination variations. Other one is neural networks. The major, in fact, neural networks have been widely used with multispectral data also, for a single reason that any time multispectral data, if you are using MLC, we can have only linear decision boundaries, whereas with neural networks, it will be possible to have non-linear decision boundaries. Second, you don't need to make any assumption about the underlying distribution of the data. In the case of MLC, it is assumed that the data distribution is Gaussian. If the data is non-Gaussian, then your MLC performance may get jeopardized. Because of these two specific traits, the neural networks are very widely used. I don't go into the details of the neural networks. This is just one of the SAM neural network classified image. Now, what is the basic underlying fact while we are trying to do classification using neural networks or the recently proposed support vector machines? The major difference between these two is what is called as empirical risk minimization, which aim to minimize learning or training error. The other one is structural risk minimization, which aims to minimize upper bound on the expected error over the whole data set. The neural networks is basically on ERM. What we try to do is, once you have created the network, we try to input the sample data, train the network with having minimal error. That is where your weights are being calculated. That is why it is called empirical risk minimization based method. Whereas in the case of SVM, it is structural risk minimization. We try to see the upper bound on the whole data set. So, I just wanted to bring the difference between these two. The other most widely used thing, as I was just mentioned, is this support vector machines. In fact, it is ironic to say that we are having very high dimensional data, and support vector machine in fact performs classification by constructing a n-dimensional hyperplane that optimally separates the data into two categories. That is already hyperspectral data, and you are further projecting it into higher dimensions. The key here is the non-linear decision boundaries that are being formed in a neural network classification method will get converted into linear decision boundaries when you project it into higher dimensional space. It is using sigmoid kernel functions, which is equivalent to a two-layer perceptron neural network option. In fact, SVM finds line or in general hyperplane that is oriented so that margin between the support vectors is maximized. This has got a small margin, this has got a large margin. The simplest ways to divide the two groups is with a straight line, the flat plane, or a n-dimensional hyperplane if the points are separated by a non-linear region such as this. This can be converted into a linear decision boundary by projecting it into a higher dimensional plane. And this is achieved by kernel functions which transform the data into higher dimensional space to perform the separation. This is a SVM classified output. The other most widely used technique is spectral feature fitting, which will match the reference spectral spectra by examining specific absorption features in the spectra. In fact, the matching with the pixel spectra is by performing a continuum removal. I will just come back to this continuum removal a little later. For doing the spectral feature fitting, the user specifies a range of wavelengths within a unique absorption feature that exists for the chosen target. Then the reference spectra are then compared to the target spectra using depth and shape. The depth is the absorption depth of the feature with respect to the reference, and the shape, the entire shape in the spectral space in a least square sense compared with your reference spectra. Now, it was mentioned that this comparison and depth estimation is performed by doing a continuum removal. Continuum is nothing but normalizing the reflectance spectra to allow comparison of individual absorption positions from a common baseline. Continuum is nothing but a convex hull that fit over the top of a spectrum utilizing a straight line segments that connect the local spectra minima. The basic idea is you want to maximize this depth position. This is your basic input spectra. If you have done the continuum removal, this curve will get flattened out. This absorption position, this will be the absorption depth. The depth of this will be compared with respect to this common reference baseline. That is the entire key. This is for a Kellanite reflectance spectra, and this is after having performed the continuum removal. Then the apparent band depth of an absorption feature relative to the surrounding continuum in a reflectance or an emissive spectrum is calculated. It will be compared with your input and the reference spectra. This is a spectral feature fitting image for alunite. This is again from Everest, Cuprite, Nevada. But the only caution while using the spectral feature fitting is, if you are looking for a feature which has got a weak absorption, then those weak absorption positions will be totally removed by the continuum removal. If you are looking at geological applications where the minerals have got a strong absorption over certain wavelength range, then using spectral feature fitting will be wise. Next comes the spectral unmixing part. In fact, mixed pixels are generated if the size of the pixel includes more than one type of terrain cover, which is usually the case, and measured spectral radiance of a pixel is the integration of the radiance reflected from all types of terrain covers within the ground instantaneous field of view, and for any finite resolution imagery, spectral mixing is inherent. It is inevitable. There can be three ways these mixtures can be happening. One is an aerial extent where there is a 50-50 mixture, where is aggregate. There could be a checkboard kind of arrangement on the ground shell, and other one is randomly oriented or intimate. We have to deal with all these kind of mixed pixels while doing information extraction from hyperspectral data sets. This is just to show a 10 meter ALI panchromatic image. This is 30 meter Hyperion image. This is actually the mixed pixel of lush growth and as well as a bare field. How do we get into the components of these two classes over the mixed pixel case? And this spectral unmixing can be defined as a procedure by which the measured spectrum of a mixed pixel is decomposed into a collection of constituent spectra or endmembers and a set of corresponding fractions or amendances indicating the proportion of each endmember present in the pixel. Endmembers, as we defined earlier, they are the pure pixels representing the macroscopic objects such as water, soil, metal or any other feature of interest. When it comes to the doing spectral unmixing or per se the taxonomy of the unmixing algorithms, there are two ways. One, you can do a linear unmixing or you can do a non-linear unmixing. But most of the literature and the tools and techniques that are available as of today, they only assume a linear interaction between the signal and the surface landscape pixel. So we will be talking only about the linear unmixing. When we say linear unmixing, what we are only trying to say is the mixture holds approximately when the mixing scale is macroscopic and there is a negligible interaction among the distinct endmembers. Second thing is, when we talk of unmixing, is it really necessary to do a complete unmixing of a hyperspectral scene? Is it possible or is it even desired? Spectrally complex and very high dimensional data are very difficult to unravel fully. The optimal way is to go in for partial unmixing, which provides a way of mapping the endmembers of interest. And many applications of imaging spectrometry can be, are my target signatures present in the scene? If so, how much of each target material is present in each pixel? The number of unmixing members is 1 greater than the number of spectrally defined target materials. And one additional endmember can be thought of as the composite of all other scene materials or everything else. That is like a background. Now, the conceptual diagram is the input image. It goes through dimensionality reduction, endmember determination. Based on the endmember determination, doing the model inversion to arrive at the abundance map. We have seen that PPI can be one of the ways where the endmembers can be defined. Now, when we say inversion, we are talking of model inversion. First, how do we build the model for inverting it to arrive at the abundance map? One of the most widely used and very popular algorithm is linear, constrained and mixing. In fact, you can have linear, unconstrained and mixing also, but we are not going to talk about linear, unconstrained and mixing. It will be only linear, constrained and mixing will be talked about, where R is your effective reflectance of the mixed pixel, RA is the reflectance of the ith material or the end member, and Fa is the spatial fraction covered by the ith material, and N is the number of materials present in the pixel. Now you have something like a form L is equal to MR plus B, which can be recast as F of I Li, where Li is the radiance from a pure pixel of the material or the end member I. If you have given M spectral band sensor with the bands designated with this J subscript, we can write M equations of the form sigma of I is equal to 1 to N F of I R of Ij in reflectance space or L of Ij in radiance space. If we can claim to know the spectral reflectance or irradiance for the materials potentially in each pixel, that is the end members, we can write M simultaneous linear equations in N unknowns, that is the fractions are the only unknowns. This is in the matrix notation. This is for a 3-band, 3 end member case. For doing the matrix manipulation, for solving for the F1, F2, F3, these will be the fractional values. However, we have to recognize that we have to put some constraints to avoid instances like negative and more than 100%. If you see this simplex, if this is a pixel which requires a negative amount of E2, which is not allowed, and if this is E3 plus, and if you are having more than 100%, which is not physically possible. So these two constraints will be added to say that the fractions all sum to 1, then this is referred to as partially constrained case. We can further constrain all the fractions to be between 0 and 1. This is fully constrained case. One of the common implementations of this linear unmixing is, as far as again it is in NV only, there is a matched filtering application, which is complete unmixing and finds spectra of end members in the scene to get an accurate analysis. In fact, what it generates the thing are two outputs it will be generating. One will be the matched filter score and other will be the infeasibility image. The higher the score, and this matched filter score image will be 0 to 1. If it is 1, it is a perfect match, and smaller the infeasibility value, better will be the result. Infeasibility is based on both noise and image statistics, indicate the degree to which the matched filtering result is a feasible mixture of the target and the background. This is the sample output. This is MF score versus infeasibility. The pixels around the red, this is for sandstone. So higher MF score but lower infeasibility. That is the combination which will give you the desired MTMF result. Again, this is a Hyperion data. It is pre and post of the earthquake in 2004. This is Montromagnet density, the sliced abundance image, and this is the Montromagnet abundance image itself. This is the way it is in 2002, where the abundances of this particular class are very low, whereas in the post earthquake case, this abundance of particular material have increased significantly. Likewise, this is in the Iceland volcanic eruption instance. In fact, here it is slightly different approach has been used. I was saying about talking about this central wavelengths at atmospheric correction as an important parameter, but the manner in which the data has been pre-processed can have a bearing on your unmixing results as well. Just to have an understanding of the relation, the manner in which the data pre-processing, for example, the atmospheric correction and the final unmixing that will be attempted with different scenarios, like if you are using different water vapor absorptions like 1135 nanometers, 940 nanometers or 820 nanometers, majority of the pixel difference is 7% to 10%, and very few pixel locations maximum difference of abundance is minus 25 to plus 22%. The abundances also can vary significantly depending upon the type of the parameters that are chosen for carrying out the pre-processing of the data. This example I am only highlighting, illustrating to say that given your geographic location, given the type of climate and the time of the year at which the image has been acquired, proper choosing of the parameters is necessary to arrive at useful and realistic abundance maps. And some of the techniques which are outlined in the last few slides are necessary for conducting quantitative remote sensing application. What do you mean by pure pixel? Given any ground instantaneous field of view, if you are taking Hyperion as an example, that is 30 meter by 30 meter, we expect that only one type of material that is present in that pixel. That is what is termed as a pure pixel. Given your spatial resolution, only one type of material will be present in that ground instantaneous field of view or in that spatial pixel. That is what is termed as the pure pixel. I hope I have made it clear. The second question is, what is the real use of data reduction in remote sensing? In fact, if you are having a large number of bands, is it really prudent to use all the bands, assuming that all the bands will contribute in information extraction, or try to search for subset of those total number of bands, let me be 100, 200 or 300, wherein the specific information which is being sought for can be extracted by compressing that 100 or 200 bands into fewer bands for faster processing, efficient information extraction, and more, you can say, the optimal utilization of the data per se. You can contact me by email, either to me directly or you can send it to HRS, which will be forwarded. Okay, what is the use of caveat in geology? I presume you are referring to the continuum removal which I am talking about. When it comes to geological applications, one need not have to worry about continuum removal, removing the weak absorption band positions. In the case of geological minerals, most of the time the absorption positions are strong enough to be retained in a continuum removed spectra. I think there is a small misnomer which people have been using principal component analysis while dealing with multispectral data as an image enhancement tool in remote sensing. That is not the only area where principal components or for that matter MNFs are used in image enhancement. The data reduction in the expense of high spectral remote sensing are not meant for image enhancement. They are meant for compressing the information that is spread over several bands into manageable fewer bands. So there is no relation of data reduction as an image enhancement, that is limited only to the multispectral data sets wherein 5 or 3 bands or 6 bands, they are just put through a principal component analysis for geological applications as a image enhancement tool. In the case of hyperspectral remote sensing, the data reduction is primarily meant for compressing the significant large number of bands into fewer bands. I think the question that is being referred to is not with the surface imaging that we often deal with. This is more to do with mass spectrograph or mass spectroscopy which we use in lab. If you are having a specific sample which you believe is the true one, you can always characterize it the spectral positions of absorption or emission, and if you are having any claim it to be a similar material, you can always cross-check that spectral profile with your true material, which is a well-known in the field of spectroscopy. So I don't foresee any difficulty in using the basic principle of mass spectroscopy that is being used both in chemical industry as well as drugs, or for that matter any other material identification issues. I hope that will answer your thing, because you are not referring to the identifying the minerals. See, the context of the lecture is different from your question. So I presume you are having a sample. You want to know whether it is true or whether it is synthetic. If you can characterize the true sample, the absorption wavelengths, then you can always compare any given unknown sample for its purity based on the absorption wavelength positions as well as the absorption depth. It is possible. It is a well-known spectroscopic principle. If participants have any more questions, they can contact me on the email that has been shown, or they can contact HRS, who in turn will pass it on to me. Thank you.